Well, thank you again. It actually was good in the sense that I follow Martin, because my emphasis in this talk is going to be towards the reconstruction of climate over the past centuries to maybe 1 to 2 millennia, based using annually resolved proxies, be it tree rings, corals, or whatever like that. And you know, whenever you do calibrations against instrumental data, of course, it matters that the instrumental data and the proxies agree in terms of the years of observations in each, and that's pretty much, I think, would be an assumption at the very least. Maybe you could allow for Martin for you know, less well-resolved series, but the point is, it's certainly nice to be able to use the optimal amount of, the maximum amount of resolution possible in the proxies. Yeah, so why this talk? And basically, this is all like talking to, you know, the preacher talking to the choir about high-resolution paleoclimatic proxies can tell us about climatic variability and change over the past 1,000 or more years. And examples are tree rings, corals, ice cores, speleothems, and laminated sediments. By no means an exhaustive list. But quite clearly, these records played an important role in the IPCC AR4 Working Group 1 report, and in fact, it was the first time that there was an explicit paleoclimate chapter. As Peck said last night, it's not clear there's going to be another, the AR5 report will have a separate paleo chapter. I hope it does, but be as it may, I think paleo is finally being recognized as a critical tool in understanding global change in both space and time. And with this in mind, it's important that we develop the most precise and accurate reconstructions of past climate in ways that also allow for estimates of reconstruction uncertainty. And Martin, of course, that was a central theme of his talk, really. And it's very important for detection and attribution studies, among other things. You know, we really need to start tightening up as much as we can in providing the levels of information that will allow policymakers and so on like that to make, you know, really tightly informed decisions on possible scenarios of future change based on the past. There was a workshop in Trieste in 2008, and these topics were really dominant themes in the summary workshop report, representing and reducing uncertainties in high-resolution proxy data. It was a workshop convened by Kim Cobb, Thorsten Kiefer, Janice Lough, Jonathan Overpeck, and Sandy Tudhope. And it's possible to go on the web and download the summary report. It's worth reading. And then also, you know, there's this relatively new project within Pages, the Pages 2K Regional Network project. And last Tuesday, there was a day-long meeting that I was a participant in dealing with this project. And I think it's fair to say that while there's different types of proxies being described for use and telling us about past climate in these different areas, to the degree possible, we want to work with well-dated annually resolved records. And as it says right here, there was a need for high-resolution proxy-based reconstructions for comparison with high-resolution Earth system models, and that's really like the, you know, the target that we want to work towards as paleoclimatologists. Just an example of some of the proxies with annual or at least near annual resolution: tree rings, of course, annually banded corals, annual ice core layers. Sometimes you can't visually see them so well, but sort of geochemically you can oftentimes discern the layers through the seasonality and certain isotopic ratios, things like that. Laminated sediments, and then also speleothems. As I say, this again is not a complete list at all, but these are probably the more commonly used records that have if not annual resolution, at least the potential for annual resolution in some cases. Just some generic principles and procedures now for high-resolution paleoclimatology. Again, this is from a tree ring perspective. That's what I am. I'm a tree ring scientist. So if I sound a little biased in that direction, you'll have to forgive me, because that's the way I think of approaching the development of proxies for climate reconstruction. And it won't apply, of course, to all proxies. I recognize that. But I think for certain classes of proxies, we should work very hard towards annually resolved and well-dated series. So high-precision annual dating, high-resolution paleoproxies should be dated by the most precise means possible. And cross-dating used to date tree rings is what I would call the gold standard. We've been doing it for decades, if not generations, and it simply works. So that's, if at all possible, that's where other paleoclimatology should work towards, is using some type of cross-dating procedure to allow for precise dating of the annual layers or bands or widths in their proxies. Replication, I can't emphasize this too much, and in fact that was a huge theme in the workshop in Trieste, the workshop report in Trieste, that replication is an absolute necessity. And by replication of the paleoproxy record to the greatest extent possible or affordable. I recognize that sometimes it's very expensive to develop even one proxy record, so it's understandable that you couldn't develop, replicate the series as much as we do for tree rings, which is comparatively inexpensive to do. But the critical thing is that replication is what enables cross-dating. And also measures of proxy uncertainty to be made. And it's basically impossible to determine the proxy uncertainty from a single record. And I should say that this is not to be confused with lab analytical error. In other words, you measure an isotopic ratio in some proxy record, be it an ice core or a speleothem. What comes out of the mass spectrometer gives you a laboratory error, but it does not tell you anything about the error associated with resampling the proxy. And you can only get a feeling for that through replication. Calibration, obviously important. Typically done directly against observed records of climate variability. This is the importance of having high resolution proxies, because annually resolved proxies can be compared against annual records of climate variability, instrumental records. It models the kind and strength of the climatic signal in the proxy used for reconstruction, and provides a measure of reconstruction uncertainty through something like the root mean square error, other approaches too, as Martin showed in his Bayesian approach. And then from a tree ring perspective, we always hammer on the issue of verification. And this is typically done by comparing the tree ring estimates of climate against either withheld or independent records of climate variability. And in a sense, it measures the accuracy of the reconstructed climate estimates against that which it should be reproducing fairly well. Now, I'm going to mainly emphasize in this talk from here on the need for high precision dating and replication before proceeding with calibration and verification methods. There are so many different methods out there that one can apply for calibrating and verifying the different proxies. And there isn't enough time to go through even a small number of those different methods. But in fact, if the series aren't really dated well and you don't have replication, you're going to be at a disadvantage right away in going to some of the very sophisticated calibration and verification methods, especially if the dating itself is somewhat dubious. High precision dating, why it matters? Well, I think it's pretty obvious from what I've just been saying. Cross dating, like used in dendrochronology, is simply the assignment of the exact counter year to each proxy value, each observation, be it a ring width, be it a coral band, be it an ice core layer, a speleothem band, something like that. I think it's at least potentially applicable to almost any annually resolved paleoproxy records. Tree rings, corals, ice cores, speleothems, laminated sediments, etc. But I would also say that it's perhaps applicable as well to less well-resolved paleo records with hopefully consistent sampling rates over time. So that just suppose your series, you can only resolve it at, say, a roughly 5-year interval. If you can do that back in time, consistently at 5-year intervals, at least you'll be able to do maybe a better job in comparing against other records from the same location. But for simplicity's sake, I'm just going to assume that the sampling rate of the proxy is 1 year here. And why it matters, and again, I'm repeating more or less what I've said before. To calibrate and verify against observed climate records, calendar years of the proxies must match the calendar years of the observed data, and also remain exact over the full time period covered by the proxy. So it doesn't do you much good if the dating is good only in the calibration interval, and then it just kind of falls apart going back in time. You really have to apply the exact dating procedures over the entire time span covered by the proxy. And this is really critical for such things as detecting changes in interannual to decadal climate forcing over time, say ENSO variability, the NAO, other modes of variability. If your dating gets increasingly off from what it should be, it's going to affect, the detection of changes in forcing. Principle of cross-dating. This is a slide from Connie Woodhouse. Really, it's pretty simple. Just matching the patterns of, in this case, ring widths or other ring characteristics among several tree ring series, and allows the identification of the exact year which each tree ring was formed. You can replace tree ring or tree with any other proxy with annual resolution. So this is a generic procedure, really, the matching of patterns of some variable from year to year. In the case of tree rings, we acknowledge the occurrence at times of some rather difficult problems with respect to dating. We have what we call locally absent rings. This ring is only partially forms around the circuit of the tree, around the trunk of the tree. And if you sample the tree here, you'll miss this ring. If you sample it here, you'll have it. And so if undetected, you'll have too few rings and a dating error in this sequence right here. In some trees, conifers, particularly conifers especially, you can have cases of so-called false latewood bands, which might appear to be true latewood bands, so that there would be a tendency to say that this is one ring and this is one ring, when in fact the total annual ring is really across this entire wide band, including this so-called false latewood band. And again, that would introduce an error. Now, you could say that, well, this is just tree rings, and other proxies may not have these particular kinds of problems, but I'm not so sure that's the case, and I think that it would be quite easy to lose track of sort of annual layers in for example, long ice core records or something like that. All this has been, recognized in the literature and written up over the years. Here's a very, very interesting paper published by Tim Baumgartner and others in 1989 on the recording of interannual climate. I can't even see it from that angle. Climate change by high-resolution natural systems. Tree rings, coral bands, glacial ice layers, and marine varves. And it's in a AGU monograph. It's really worth reading. And one of the things that Tim and others and co-authors did was to show what would happen if you pretended to have a proxy series that was well correlated with the Southern Oscillation Index. Here's the same index, but with noise added to give it a correlation of 0.7 with the actual series. Now suppose you introduce at random dating errors in this synthetic proxy record. You randomly subtract 1 year data, randomly select 2 years of data, or 3 years of data, or you do the opposite and you actually randomly add observations 1 year, 2 years, 3 years, okay? And then you correlate that degraded series against the original Southern Oscillation Index with the expectation you should be getting a correlation of 0.7, okay? Well, and you do this 100 times, and here are the box plots of the results. And what you see is a very, very clear degradation in the identification of the signal and the strength of the signal. And you actually end up getting smearing of the potential smearing of the signal, and also spurious lead lag correlations caused by the misstates. So this is one example of showing why precise dating really matters. Another paper written by Hal Fritz and Tom Swetnam, again in 1989. It was a very good year for these kind of things. It was in a paper called Dendroecology, a tool for evaluating variations in past and present forest environments. But it applies, of course, to climate too and that sort of thing. And what they did was take a collection of tree ring data that had been properly cross-dated and with missing rings properly assigned to certain years that had been missing in the wood specimens, dated. And they said, well, what if we then strip out the missing rings and recreate the chronology, assuming that we just counted the rings back in time and didn't know about the missing rings? What would happen? And so the black represents the tree ring chronology that's properly dated. The red represents the tree ring chronology after stripping out the missing rings that had been assigned independently sometime earlier. And what I'm going to show you is how that affects the properties of the data, both in the high and low frequency domains. Here's the 20-year low-pass filtered version of the chronology. The black represents the correctly dated chronology. The red, the MDT, represents the purposely misdated chronology after the missing rings were stripped out. And for a 20-year low pass, you can see that there isn't that much of a change between the two records. And in fact, the correlations in these different 50-year time periods remain pretty high overall, typically in the 0.8, 0.9 range, when in fact they should be 1.0, but still pretty high. But you look at the 20-year high pass, and very high in the beginning, and then as you accumulate misstates in the series back in time, you can see a catastrophic decline in the correlation between the two series. So by the time you get back to before 1600, you actually have a negative correlation between the two series when they should be correlated at 1.0. And so very quickly the misstates begin to degrade the high frequency side of the tree ring series. And you can look at this in the frequency domain using wavelet analysis. Here's the original tree ring series properly dated, and the wavelet spectrum right here. You can then look at the same series after it's purposely misdated. You can see the way in which the purposely misdated series gets increasingly low frequency in nature, and the year-to-year changes basically disappear. And that translates into a wavelet spectrum that shows a complete collapse or loss of high frequency variance relative to the original series. Low frequencies are more or less the same as we saw before in the low pass filtered series. But the problem is that if you were to take this series right here and say, well, let's look at changes in ENSO variability over time in the 2 to 7 year band, roughly speaking, you basically can't do it legitimately, because this change in high frequency variability over time that's been induced into the series erroneously by misstating could result in correspondingly erroneous interpretations about changes in ENSO variability. So it's really important that when you're working with high frequency climate variability and you want to compare it against high frequency modes of climate variability, the dating has to be right. So the moral of the story in part one is time and frequency domain interpretations of a proxy are only as good as the dating, not surprising. Some form of cross-dating like used in endocrinology is highly recommended, but it requires replication to do that, and that's the key thing. Cumulative misdates in an annually or near annually resampled proxy can result in a form of time-dependent smoothing and an increasing loss of high-frequency variance on interannual to decadal timescales back in time. For annually or near annually sampled series, the cumulative effect of such misdates will quickly degrade the ability to accurately detect, describe, and model changing modes of interannual to decadal climate forcing, like ENSO and NAO. When the misdating approaches the sampling rate of the proxy. That's the key thing, is that you're looking at ENSO variability, which is not that much longer than the sampling rate of the proxy. So the misdates will very quickly degrade any chance to look at changing ENSO variability over time. Now on to kind of the part two, proxy replication, why it matters. Well, it's pretty obvious from what I've been describing so far. Multiple independent records, by replication I mean multiple independent records of the same proxy collected at the same site, location, and environmental setting that can be compared in time. So it's one thing to compare, records from scattered around the world for kind of synchronous variability. We see that with, with ice core and speleothem records, looking at Heinrich events, Dangot-Oeschger events. It's totally legitimate. But I wouldn't call it replication. It's kind of a verification, or you might say, of commonality of signal or large-scale forcing. But in terms of replication, I'm really emphasizing the need to sample at the same site location and in the same environmental setting for comparison of the samples. Sampling the proxies this way allows for them to be averaged together after precise calendar year dates have been assigned to concentrate the common signal due to climate and average out the noise. And as I say here again, I would regard this as the single most powerful way to concentrate the common signal. Having a replicated record that can be legitimately averaged together through precise dating has an enormous power to concentrate the signal in ways that make it much more reliable to interpret. And it gives you also a chance to estimate what I call true proxy uncertainty in the sense of sampling uncertainty and not, again, lab analytical error. Is impossible to estimate without replication. Now, there's just some nice pictures of kind of a faux replication thing. Here's me many years ago when I was much younger in Tasmania, core in a tree, taking cores from corals, from ice cores. To give you an example of how powerful cross-dating is, here we have 6 of the series used in that previous example, the Sorrel Peak misdating example that I showed you earlier. And I just took 6 series out from 6 different trees. And as dated, we can look at the correlation between the series at 50-year time periods with 25-year overlaps. And you can see, and this is actually the correlation of each series against the average of all the rest. So it's a little different from just a kind of a bivariate correlation comparison. But the point is that you get enormous, commonality of signal that you see here across all 6 trees when properly dated. You take the same 6 series after I had stripped out the missing rings, and the average correlation amongst all series drops from 0.81 to 0.22, and you can see that all the red correlations are those below 0.4, and some go negative even though they do cross date. So this again shows the power of cross dating for testing for you might say, the synchronous agreement and calendar year dating between records from the same site and the same growth environment. And as I say here again, my mantra again, misdates are not possible to determine without replication. Any one of these series could have been accepted as being properly dated, even though it wasn't. And you wouldn't be able to tell unless you compared it to other series at the same location. And in terms of uncertainty of the proxies, here's those 6 series, okay, with bootstrap confidence intervals calculated for them. And we can look at the 20-year low-pass filtered confidence limits just because it's easier to see. But here's for the correctly dated series, and here's for the incorrectly dated series. And you can see that the confidence limits, not surprisingly, are much wider. So, you can see that, in terms of proxy uncertainty, right away you're doing a much better job when everything's properly dated. And there's other ways to look at the uncertainty in terms of signal strength estimates based on kind of average correlations between series. And here again is for the correctly dated series, the average correlation between series at 50-year time periods, 25-year overlaps, is around above 0.5 typically. And a measure of the signal strength with respect to the theoretical population series that could be had if you could core an infinite number of trees, shows a very stable high value here, which is what you'd expect. For the incorrectly dated series, you can see that the average correlation between series just collapses, particularly in the middle portion of the series. And once again, if you looked at this using some of the typical software we use in dendrochronology, you would immediately say we got problems because there's just no way that you could accept a series that has this kind of average correlation between series collapsing like that. So the catastrophic loss of signal strength in the misdated series is showing up in both for the running average correlation, the R-bar, and between series and the express population signal, the EPS. In contrast, the correctly dated series show a highly stable R-bar and EPS, indicating a believable series over time. Okay, so I've just been hammering away with tree rings right now, and maybe some of you are wondering, well, gee whiz, aren't there some examples from the other proxies that could show us that this works, that these procedures work as well? And the answer is yes. There's been some very nice papers published over the past several years on using dendrochronological techniques for dating and analyzing coral records. This is the first one that I found. I'm not claiming that I've at all done an exhaustive literature search on this stuff, but here's one paper published in 2003, chronological control of coral records using luminescence lines and evidence for non-stationary and ensotel connections, so on. And Erica Hendy and others, and Mike Gagan and Janice Lough, actually were able to show how you could match up luminescent bands to the annual year of formation in different coral records from the Great Barrier Reef, near Pandora Reef and that sort of thing. And they even came up with a scheme for generating what the so-called luminescence band skeleton plots, similar to what we use in dendrochronology for dating tree rings using skeleton plots. So they borrowed the methods of dendrochronology and applied them very successfully. And I should say one reason for this is that Janice Lough worked in Tucson at the Laboratory of Tree Ring Research for several years with Hal Fritz, so she kind of learned that all about that perspective while working there. And so here's the final thing. They showed here's a luminescence record for 2 different corals, and then they had other coral records too, and then they created a master series after correctly dating all the individual luminescence records using their skeleton plot procedures, and then related it to river runoff for the Burdekin River, and came up with an amazingly strong relationship between river runoff and luminescence in the corals that's related to humic acid coming down the river and into the near-shore barrier reef coral colonies. And the conclusions from this study, this is a verbatim quote, this study has demonstrated for the first time that the cross-dating techniques adapted for dendrochronology can be successfully applied to coral records. Such an approach can ensure accurate dating of coral records. And then this study has demonstrated for the first time that, the study also highlights the need to combine records from more than one coral record to ensure dating accuracy and so on. So it can be done with other proxies. And so as early as 2003, we have an example from the coral community that tree ring dating methods can be applied. And then Janice Lough actually, in the following year, published another paper, I should say, that basically repeated the same things, and which she recommended some level of replication, ideally at least 3 records for come up with a much more robust indicator of climate variability from the abandoned coral records. And then there was a paper in 2007 by Kristen DeLong, Terry Quinn, and Frederick Taylor, again using tree ring techniques for developing a replicated coral record from New Caledonia. I won't go through this too much longer, but they also used some methods of tree ring analysis for measuring signal strength, what we talked about, this expressed population signal. And without going into details, they found that for their coral records, 3 series was right to produce a coral record with an acceptably strong signal, common signal. And I put down here Janice Lough wins. She was saying at least 3 series, and that's exactly what Terry Quinn and Kirsten found too. And 3 records, I wouldn't think would be too onerous of a task to. With respect to replication. In tree rings, we might sample 10, 20, 30, 40 trees because there's a lot of noise in tree ring series. Here, you can get away with only 3 and really improve the strength of the signal. And cross-dating also allows you to put series together back further in time. Here's an example from Kim Cobb. Uranium thorium dated fossil coral records spliced together and more accurately than the uranium thorium dates themselves allow for. And there's even work now in extending these procedures to clams, for mollusks in both the Atlantic Ocean and in the Pacific. Here's a case, the first cross-matched floating chronology from the maritime fossil record, data from the growth lines and the long-lived bivalve. And it just shows, the way in which they use cross-dating to actually realize that, for example, this series was off by 8 years and had to be adjusted appropriately, and this one was off by 1 year. So again, the methods can be applied, I think, far more generally than have been in the past to different paleoclimatic indicators with annual resolution. And then finally, last slide before the summary, you might say, very recent work by Brian Black and others with the geoduck here in the Pacific Northwest, using tree ring cross-dating techniques to properly assign exact annual calendar years to the growth bands of the geoduck. And this shows you, this is quite amazing, shows you the level of error that you would get if you simply counted the growth bands back in time. The age error is at 432. Only about, I think, 20% of the series would have been correctly dated just based on counting the bands back in time, whereas you'd have others with errors as much as 10, 20, or even 30 years. So, moral of the story part 2, and then I'll finish, then I'll be done. The only way to establish precise counter year dating of high-resolution paleo proxy records is through some form of cross-dating, and that requires replication. Estimates of signal strength and proxy uncertainty are possible if replication is done. When possible, the basic principles of tree ring dating ought to be applied to the development of other high-resolution paleoclimatic proxies and climate reconstructions from them. Examples extracted from the coral and mollusk growth band literature indicate that this can and should be done. And the additional time and expense incurred to produce precisely dated and replicated proxy records is worth it, because more trustworthy and interpretable proxies and climate reconstructions from them will be produced. And with that, I thank you, and I'll take on any questions that you might have.
We have time for a few questions. Okay, there is one question there.
Yes, Ed. How does cross-dating let us know something about the environmental signal that we're getting? I mean, if you just have one series, for instance, you don't really know if it's an environmental effect or.
The existence of cross-dating between individuals in a sort of a given environmental setting and population simply tells you that there is a common sort of growth limiting or common environmental signal contained in the series. It doesn't tell you anything about what's causing it. It could be climate, it could be insect infestation in trees, it could be whatever, something else. But so it's only really intended to enable you to assign the correct count of your dates to the series. Once you've done that, then you can go through, explicit calibration exercises to try to identify the nature of the signal that's in the replicated proxy.
Ed, as a non-tree ring person, I think we get your message here. Then, if you translate it to the number of, say, Northern Hemisphere reconstructions we've been seeing, some people call them spaghetti diagrams and so forth, how much of that variability would you attribute to people not adhering to your sort of Bible of procedures versus regional sampling problems versus other regional environmental signals, etc.? So for the non-ingrained people, how do we interpret the variability of those very commonly shown and much publicized reconstructions?
The majority of the hockey stick and its variants, since then, at least most of them have been based on tree ring data, which we more or less at least assume, if not know for sure, personally, are accurately dated, or precisely dated. When you get into the issue of bringing in sediment records, finely sampled but still maybe decadal resolution sediment records with much more uncertain dating, then of course that would add a level of uncertainty I'm not sure how I would know how to estimate it, but it certainly could. I think the record by Anders Moberg, for example, has he purposely selected a lot of non-tree ring records to provide kind of an independent estimate of temperature variability for the Northern Hemisphere, and it included, sediment records. You'd have to go back to the literature and find out exactly how they did the dating, and so on like that. But with the tree ring data, I would say that the dating itself would not be the source of uncertainty that you say. It's more related to something else, maybe the tree ring series just aren't expressing the same signal that you think it should be in terms of, temperature variability.
Okay.
Okay.